Getting tomorrow's technology ready for the future is the purpose of the Technology Demonstration Missions Program. Taking today's most promising exploration technology and raising it to the level of maturity that mission planners require means that TDM puts the technology to the test. The projects include communication, materials, propulsion, and robotics. Key to any exploration program is effective communication. Current technology is hitting a bandwidth and wavelength ceiling. Tomorrow's missions will need a new technology. NASA is leading the effort to make laser light reinforce the current radio or RF-based communications. The Laser Communications Relay Demonstration, or LaserCom project, will provide an orbital test bed for a wide variety of scenarios to simulate future missions. In the near future, laser communications could increase the amount of information to tens of gigabits per second. This would be an improvement of data rates of between 10 to 100 times. The project will use laser light transmitted to a satellite payload and back to an Earth station to simulate and test a large number of possible mission scenarios. Another foundational technology being improved by the TDM program involves a basic component of all exploration missions: time. The Deep Space Atomic Clock project promises to reduce cost, improve space navigation, data quality, and the next GPS system. To test this concept, the project will fly the Deep Space Atomic Clock along with a GPS receiver on a commercial communication satellite. Ground-based systems require two-way communication. With an onboard atomic clock, DSAC allows for one-way navigation using NASA's Deep Space Network more efficiently. Eventually, this will enable deep space autonomous navigation. Communications and science payloads need advanced warning of solar flares. One way to do that includes station-keeping capabilities like the current NOAA Solar Activity Warning Instrument. The TDM Solar Sail project takes a previously tested propulsion technology and infuses it into an even better warning system 2 times closer to the Sun. The Solar Sail project pushes the technology to a practical application while simultaneously maturing the system so that future mission planners can choose it for a whole range of missions. All of NASA's technology demonstration missions are infusing mature technology from the realm of tested to ready and proven. But one of those demonstrations tests the very materials used for spacecraft construction. That project is a continuation of a heritage project called MISSI, Materials International Space Station Experiment. Building on the previous missions, MISSI-X seeks to provide low-cost access to space technology experiments using robotically installed plug-and-play features. MISSI-X plans to monitor the payloads by collecting data and photographic images in near real time. This allows for faster testing of materials and greater opportunities for educators to have easy access to the ISS as an experimental platform. Maturing materials and technology continues to be an objective of the TDM program. Sometimes that means putting instruments on the spacecraft of other NASA missions to further our collective knowledge. One project that does that is MEDLI. MEDLI stands for Mars Science Laboratory Entry, Descent, and Landing Instrumentation. MEDLI is an instrumentation suite embedded in and behind the heat shield of the Mars Science Laboratory, now on its way to a Martian landing this summer. The instruments gather real-time data on the atmosphere, thermal protection system, or heat shield, and aerodynamics during entry and descent. The MEDLI data will improve modeling and predictive capabilities for future missions, ensuring safer and less expensive missions to a larger variety of destinations. Along with the MEDLI data, NASA will see the fruits of research into entry in low-density atmospheres, like Mars, with the Low Density Supersonic Decelerator, or LDSD project. On Mars, for example, increasingly massive payloads and eventually human missions will require new ways to slow down to subsonic speeds high in the thin Martian atmosphere, allowing more landing site options. These heavier spacecraft will need large drag-generating devices, and the LDSD project will test 3 of them. 2 of the test articles will be inflatable inner tube type devices that surround the entry capsule. These 6 and 9 meter devices will be flown at supersonic speeds high in the Earth's atmosphere. The 3rd device will be a large 30-meter parachute tested several times to collect data for future exploration missions. All the previous exploration-enabling technologies will be dependent on propulsion to get to their destination. Long-duration missions require special considerations for the cryogenic propellant likely to be used for human exploration missions. On short missions, the natural boiling off of cryogenic fluids is not as serious a concern, but on long missions it becomes critically important. Propellants are heavy and expensive to lift to orbit and therefore too precious to lose. Anything we can learn to minimize this pays back huge dividends. There are a variety of approaches to meet this challenge, including passive systems like insulation and active ones like refrigeration. Another important part of this research is lossless transfer of cryogenic fluids and accurate measurement. Once completed, the flight demonstration technology projects will be extremely valuable, enabling us to reach our exploration goals beyond Earth orbit. As we begin to land even more ambitious crewed and robotic missions, one of the most challenging aspects of those missions will be landing in a large variety of conditions. The Autonomous Landing and Hazard Avoidance Technology, ALHAT, uses sensors to rapidly map the ground in 3D and measure range and velocity far more accurately than existing radar systems. ALHAT has already made tremendous strides in meeting the challenge of safely landing in some very difficult terrain. In the near future, ALHAT will be integrated with a vertical test bed named Morpheus to test and demonstrate advanced propulsion and safe landing techniques, critical for future missions. Some of those future missions will include humans, others robots, and some will be a symbiotic combination of both. The Telerobotics project is working on board the International Space Station, integrating robotics seamlessly into the nation's space exploration goals. From measuring environmental conditions on the ISS with free-flying robots called Smart Spheres, to dexterous two-armed humanoid robots like Robonaut 2, NASA sees a growing role for intelligent robotic devices. Telerobots can also save precious resources by doing extravehicular activities, working before and after humans. Each of these programs has been carefully chosen because they contribute critical technology and functional knowledge to our nation's exploration objectives. They improve safety and reduce cost. The Technology Demonstration Missions Program provides new knowledge and capabilities needed to enable NASA's future missions.
Remember these? Laser light made records obsolete. NASA is on the verge of doing the same thing with space-based communications. Before the end of the decade, the Laser Communication Relay Demonstration Mission will revolutionize the way we move tons of data from orbit to ground and all around the solar system. The demand for vast transmission capability grows exponentially. Sensors are gathering more data than ever. Sophisticated command and control software talks more and asks more. Conventional radio frequency transmissions can't meet the need. That's why engineers at Goddard and partners like MIT Lincoln Lab, the Jet Propulsion Lab, and Space Systems Loral are working on the next generation of high data rate, low mass optical systems. Their goals are nothing short of imagining the future and bringing it to life. Imagine live, high-definition video feeds from faraway places in the solar system. That's the promise of LaserComm. The beauty of LaserComm is its scalability. Missions will see profound improvements, with speeds increasing from 10 to 100 times over today's RF transmissions. And huge bandwidth improvements are just the beginning. Reductions of hardware mass and power demands will see equivalent savings. Smaller communication systems mean more efficient power management, and more efficient power management unlocks a wealth of potential engineering options for other systems. LaserCom is just one part of NASA's new initiative to commercialize space. This particular demonstration will hitch a ride on a Loral communications satellite in 2017. Once on orbit, control of the optical module will be turned over to NASA Goddard for testing. Two-way data transmissions from ground stations at White Sands, New Mexico, and NASA's Jet Propulsion Laboratory in California will put the system through its paces. But just a few years after a successful demonstration, NASA's own telecommunications relay system could be replaced with the more advanced hardware. Data transmission by laser light. That's a bright idea. And as a means for moving huge amounts of data efficiently and effectively, it's the communications backbone of ambitious plans for the nation's future in space.
The landmark Vehicle Assembly Building at NASA's Kennedy Space Center in Florida is getting a renovation so it can remain a fixture of America's space program. After almost 5 decades stacking and processing Saturn V's and the Space Shuttle fleet, the VAB needs improvement on a grand scale to service new launchers expected to debut in the next few years. The new designs include the Space Launch System, a massive rocket intended to return astronauts to deep space. The building also will be set up to host commercial rockets that are much smaller. With that in mind, engineers from the Ground Systems Development and Operations Program have designed flexible systems that can meet the needs of several different kinds of boosters. They also are making provisions for handling spacecraft, including NASA's Orion, now in development. But much of the work will focus on replacing wiring, cables, and fire protection system piping to meet modern standards and increase reliability. Already, 70,000 feet of cabling have been pulled out of the building's cable trays. In all, 50 miles of cables will be removed. Most are bundles of copper wiring that were common in 1965 when the VAB was constructed. Now, it only requires a couple of fiber optic lines about as wide as a finger to meet the needs of rocket processors. 7 huge platforms bolted in High Bay 3 to service the Saturn V will be removed to make room for modern structures, each weighing about 90,000 pounds. The new platforms will be outfitted with everything required to process a rocket and spacecraft. The focus is to upgrade the VAB for a new generation of launchers and missions to allow NASA and its partners to continue to meet national goals of space exploration.
Since the beginning of the space age, NASA has explored our solar system, bringing back unprecedented scientific knowledge. But only a handful of these missions over the past 50 years have actually collected and returned samples from these far-off places. Astronauts on the Apollo program traveled to our moon, bringing back over 800 pounds of moon rock. Stardust was an unmanned mission that collected samples from the coma of Comet Bielt 2 before returning them to Earth for in-depth scientific study. OSIRIS-REx is the most recently funded sample return mission that will launch in 2016 and return surface samples from an asteroid in 2023. The Comet Nucleus Sample Return mission will collect subsurface samples from a comet and return them to Earth. Comets and asteroids are leftover remnants from the early solar system, and by studying samples from these objects, we can learn more about the formation of our solar system and may find clues to the origin of life on Earth. Collecting a sample from a comet is a challenging feat for many reasons, including how far away they are from Earth and how little gravity they provide. In our concept, harpoons are used to collect and retrieve samples from interesting locations on these exotic objects. Traditionally, when collecting samples on Earth, we use scoops, shovels, or coring drills. But on comets and asteroids, there's so little gravity that you would push yourself off the surface if you used one of these methods. Harpoons allow you to grapple to the surface while taking a sample, allowing rapid sample collection and retrieval. First, we choose a specific interesting area to take a sample from, and then fire a sample collecting harpoon into that spot. As the harpoon penetrates into the comet, it fills its inner sample cartridge with subsurface material as it goes deeper. When it reaches its maximum depth, the sample cartridge closure mechanism shuts, trapping all the material inside it. The sample cartridge is then withdrawn from the outer harpoon sheath and pulled back into the spacecraft. The sample is then brought back to a terrestrial laboratory where scientists examine the collected samples in a pristine environment. Before we journey here, we need to work here in the lab studying comet and asteroid analogs. In order to determine how much energy is required to penetrate different depths in various density material, we've designed and built a harpoon test laboratory. Although the actual mission will use a cannon, for safety reasons we've employed a ballista to fire the harpoons. By correlating the imparted energy versus the penetration depth, we will know how to size the explosive charge for the actual mission. The Harpoon Lab allows us to study how the tip geometry, cross-section, and the mass of the harpoon affect its penetration. This has allowed us to optimize the harpoon sheath for a range of possible comet densities. Although sample return missions can be quite costly and complex, they offer important advantages over missions that study their subjects from a distance. Sample return missions allow terrestrial laboratories to study in far greater detail with a variety of techniques, and can even be studied by future generations with technologies that have not been invented yet.
If you wanted to find out how tall mountains are on other planets, how would you do it? If you're on Earth, it's easy. You can take a picture, fly over the mountain, or you can actually go there and measure how high it is. On other planets, it's much more difficult. You might be able to estimate height using shadows, or even take 3D pictures from a satellite. But what if you wanted to know what the mountain looked like as a 3D model? To find out, NASA scientists can use a precise measuring tool called LiDAR. Mounted on a satellite orbiting high above a planet, LiDAR instruments are able to accurately measure the distance between the instrument and the landscape below using laser pulses. To make these measurements, the LiDAR instrument first sends a laser pulse down to the planet's surface. The pulse hits the ground and reflects back to the instrument, where an onboard counter measures the time it took the pulse to make its trip. That gives a precise measurement of the distance between the instrument and the ground with respect to the planet's gravitational center. As the satellite passes over the landscape, the instrument sends out a series of regular pulses. By recording and combining these measurements, scientists can use the instrument to gradually build up a map of the height of the terrain. After many more measurements, the end result is a high-resolution 3D model that scientists can view as if they are actually on a planet flying over the terrain. They can then study its shape in more detail, looking for clues to the relative ages of craters, the shape of valleys and landscape features, and much more. But LiDAR is far more versatile than simply measuring the shapes of mountains and craters. Earth scientists, for example, use LiDAR to measure the height and density of the Earth's forests. Others use LiDAR to study small changes in the heights of the Earth's major ice caps over time. Still other scientists use LiDAR to study the composition and structure of Earth's atmosphere, as well as the atmosphere of other planets. And they can do all that without ever having to climb a mountain.
Space has always and always will lead right through the great state of Florida.